Reminder that I have given you the option to do test corrections on the first test. They're going to be due Wednesday, which is the next time we meet, because this is a long weekend. I won't see you Monday. Yeah. So the next time I see you will be Wednesday the 15th. Test corrections will be due that day. And copy the problem on new paper, show all your work, circle the new solution, write a sentence or two about what happened, and attach it to your unchanged original test. Don't change anything on the original so that I can compare. Okay, and then just a quick look at the syllabus so you can see what else is coming up. We're going to talk about exponential functions today, so there's actually not much calculus happening today. This is one of those embedded review days. So we'll review exponential functions right before next class, which we're going to talk about exponential derivatives. And then we'll have a project check-in day and another quiz coming up the following week. The 20th of October, yeah, and that's a take-home quiz, just like last time. Yeah. Okay, so today we're going to review exponential functions so that we can find and use derivative formulas for them next class. So review day. So let's suppose an air freshener starts with 30 grams and evaporates. Let's write a formula for the quantity Q, grams of air freshener remaining T days after the start, if the air freshener decreases by 2 grams per day. What would the formula for Q look like? Q equals what? I start with 30, and I'm losing 2 grams per day, so minus 2t. Yeah. What kind of function is that I just wrote? Linear. Good. Okay, so let's write another function, but this time we're going to describe the way that the air freshener decreases is 12% of it is used each day. So Q equals, how do I, it's not 30, or, yes, so you could either do 30 minus 0.12 times 30, T, right? But if you're subtracting 12%, that means you are keeping 88%. Yeah. So I have 30, and I'm going to multiply that 30 by 0.88 each day. So how do I denote repeated multiplication to the t power? I multiply by 0.88 each day. So multiplying by 0.88 once, you would just multiply by 0.88. If you're going to multiply by 0.88 twice, you would multiply by 0.88 squared, right? So this is 30 times 0.88 to the t. And that is what we call an exponential function, because the variable appears in the exponent. So exponential functions have this form, p of t equals p naught times a to the t, or p sub 0. You can read that either way. When I say naught, it's the N-A-U-G-H-T, like nothing standing for 0, p naught. So P naught is the initial quantity. The starting amount in our example was 30, initial quantity. And A is called the base. We're going to insist that A be positive and A not be 1. Okay. And if A is bigger than 1, what kind of exponential function do we have? Growth. And if A is less than 1, like in our example, because 0.88 is less than 1, what kind of exponential function? Decay. So instead of writing P of t equals P naught times a to the t that uses base A, we could instead use base E. You can always write an exponential function in either form, where P of t equals P naught e to the kt. And this equation is used whenever you see the phrase continuous growth or decay. That word continuous means use the formula with the E in it. Okay. When k is positive, we have exponential growth. When k is negative, we have exponential decay. Well, t is the variable. So t is you would input different numbers for t for different amounts of time. So k is a constant that would stay the same always. Yeah, so we're going to actually do that in number 4. Yep. But just in case people have forgotten, e is an irrational number. It's like 2.718 blah, 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 blah. It's like one of those numbers like pi. Irrational has an infinite decimal expansion. And its derivation, where that number comes from, will be found in the activities. Because I know some of you asked me in the summer where that number comes from, and I was like, wait till calculus. So you'll get to see it today. Yes. Well, not necessarily. We could go backwards in time. Right. Yep. So I think this example might help with the k positive, k negative thing. So if I wanted to know the continuous decay rate, that's the number k. We call k the continuous decay rate. That corresponds to the 12% decay rate from question 1b. So I have 30 times 0.88 to the t. And I need to know, how do I make that equivalent to a p naught e to the kt formula? So p naught's the same, e to the kt. So to make those two equations the same, the 30s don't matter because they're the same on both sides, right? T doesn't matter because it's the same on both sides. So it turns out that 0.88 has to be the same thing as e to the k. And how do you solve that thing? The ln of both sides. Yeah. So if I take the ln of both sides of this thing, the ln of 0.88, what is the ln of e to the k? K. Yep, and then we could get a decimal for the ln of 0.88. Negative 0.128. And see, it came out negative, right? The reason the k came out negative was because this is an exponential decay problem, right? If that 0.88 had been a number bigger than 1, like this was an exponential growth problem, and I had a 1.2 there, that k would have come out positive. Negative k values correspond to a values that are smaller than 1. And positive k values correspond to a values that are bigger than 1. This sounding familiar? Okay. Nope, k is the ln of a. K is always going to be the ln of your base. And a is always going to be e to the k. So if you want a little shortcut, a is always equal to e to the k, and k is equal to the ln of a. But you don't have to remember that because you can always just write out like what we did here and figure out what a or k has to be. Maybe you're thinking of something else. Yeah. Okay, so let's sketch a generic exponential growth curve and a generic exponential decay curve. What's an exponential growth curve generally look like? Whoosh. Yep. And this right here, what is that usually? It's 1 if you're just doing a like a to the t. What is it for p naught times a to the t? P naught. Because this is the y-intercept. That's the y value you get when you plug in 0 for t. If you put a 0 for t in here, a to the 0 is 1, and you just get p naught. So that is p naught right there. So this is a growth, exponential growth. And then exponential decay, what does that look like? Right? Reflect over the y-axis. This is still p naught. Those look like familiar functions. Drawn stuff like that before. That's it. Now you're going to do some work to help you remind yourself of all the details.